Hey, what's up, everybody? This is Coach Simpson. Going to get you guys through lesson 36. Exponential functions is what we're going to start with this lesson. So we'll go ahead and jump right into it. Now, understand exponential functions aren't really too bad. All right, you have two different type right here. If you look, you got exponential growth. Get this draw tool. Okay, you got exponential growth, and then you got exponential decay. Now, it's pretty easy to understand what the difference of the two is. Growth, if you look right here, this left side right here, it basically tells you that the base is greater than 1. So this function represents a growth. So basically, you're looking for any number greater than 1. And anytime this number is greater than 1, you can consider it a growth. And then a decay is between 0 and 1. So basically, any fraction or decimal type numbers right here will give you a decay. Now, the general form to write these out is y, okay, equals, all right, the letter b for base, and then your x now is your exponent. Okay, so it's pretty simple to understand, and it goes from there. And then again, if your b, your base, is greater than 1, okay, again, this is when it's greater than 1, okay, the function represents, we just talked about it, this would be a growth, okay. All right, then again, if b is, I'm just going to write the symbol this time, if it's less than 1, okay, or really, it's not really less than, let me erase that. Really, it's when it's between, okay, when b is in between 0 and 1, okay, it's a decay. If I can spell. It's just hard to write on this screen. Okay, so basically that's exponential growth in a nutshell. Again, it's not too hard. Basically, the biggest thing you're trying to understand is what is you're looking at the basis and then where it falls. Okay, now you look at this example. They just want us to match each graph with its corresponding equation. State whether each function represents exponential growth or exponential decay. Um, Again, when you're doing these, you can use Desmos if you need to. And then if you understand, the bigger the number, the steeper the line will be. So like, for example, um, if you look between these two right here, you know they're both growth because they are going up. But this one's much steeper, so the base should be bigger than this base. Same thing here with your decay. Since this line is going down, this one's going down. It's whichever one goes down faster, basically. That's kind of how you can tell which one is a smaller number. Basically, the smaller the number, the taller the graph on decay. All right, so we kind of already just described these. This one right here is a growth. And again, since it's not as steep as this one right here, if you look at your growths down here, 1.2, that's greater than 1. 3, that's greater than 1. So both of these are growths. I know that this one has to be A just because of the fact of it's not as, again, that line's not going up fast. Okay, if you think about exponential growth, something that's growing really fast, so the bigger the base, the higher it's going to grow. All right, so this right here would have to be B. Again, we know that's a growth. Again, these are decays because they're going down. So it's pretty simple. Okay, again, so now this is 1/4 or 0.25, and this is 0.7. So it's between 0 and 1. But since this is a smaller number, I know that one's going to be C, and then that one's going to be D. All right, and again, it just has to do with those numbers right there. So really, when you're dealing with exponential growth and exponential decay, it's not a hard concept. You basically just got to understand what numbers are bigger than what numbers are smaller. Okay. Now, there's another type that's not just a base, like a random base. It could be base 2, 3, 4, 5, whatever you want it to be. And then they come in this one thing called Euler's number. Okay, it's E. It's just a different thing that when you're dealing with exponential type numbers that you can recognize. And it basically, like I said, it's called Euler's number. All right. Basically, what Euler's number is, again, it's an irrational number. So basically, it's a number that they found in math, and basically, you can use it to help with these type of things. This is just an irrational. Again, if I could spell, I'm actually going to type this one. Okay, see if I can type it better. Okay. Okay, irrational numbers basically are real numbers that cannot be written as a fraction. Okay, so on and so forth. And then again, if you look right here, this is Euler's number. And basically the way they represent Euler's number is just a little e, okay? And again, it approximately equals 2.718, all right? Again, if you need to understand the way Euler's works, okay, you could rewrite it as 2.718 in place of e, but my opinion is just keep it as Euler's number. That won't make it too hard. Now, understanding growth and decay with base e, it changes up a little bit now. Let me delete these things right quick. It changes up just a little bit. Instead of it being greater than 1 or between 0 and 1, now basically if the exponent up here in front of x, okay, this I'll go ahead and draw right here. If this part right here is positive, okay, and it talks about it right here is greater than 0. Basically, if it's positive, all right, this is a growth, okay? So that would be a growth. Now, if this number is negative, this exponent number in front of x is negative, okay, then that's a decay. So that's how you could kind of tell the difference between the two, okay? So again, if you think about exponential, again, if it's greater than 1, okay, it's a growth. If it's between 0 and 1, it's a decay. Now, when you're talking about Euler's number, when it's positive, it's a growth. When it's a negative, it's a decay. So it's pretty easy to understand there. All right. Now, on this example right here, they're going to want us to basically break this down and graph it and go from there. Now, domain and range on these, basically the way domain is going to always be all real numbers here. So again, we could just easily put the capital R here. All right, that double R. All right, so that's easy for domain. Oops, made that too big. Maybe all right. Now, range is going to always be, range here will be y is greater than 0. And again, we didn't talk about this, and it's about to come up here in a minute, that word asymptote. Basically, exponentials all have asymptotes on the x-axis. So basically, this line right here that I'm drawing right there, logarithmic, or not logarithmic, but all these exponentials, Euler's, and all these all have the same asymptote. So basically, you would never cross this x-axis unless you have some transformations. Okay. And then an important point here that doesn't have any x-intercepts, like I said, because you can't have them right now. But the important point that we need to focus on, and I'll put x-intercept. Right now it has none. Okay, but the y-intercept is an important one. All exponentials in Euler's all have this y-intercept at 0, 1. So basically, this is kind of where you this is basically kind of where you can start your graph from every time is at 0.01. And then again, that asymptote I was talking about, that's y equals 0. Okay, if we want to fill in the table, zero point 0.04. This one right here could be 0.14. This one right here could be 0.37. This one right here could be 1. 1 is 2.7. 7.3. Oops. 7.3. And this one right here is 20.08. Okay, now, like I said, whenever you're doing these, it's pretty easy to understand. This is the way I kind of remember it, is your first point can always be at 0, 1, okay? Your second point at anything to the 1 exponent is basically gonna be whatever the base number is. So, for example, our base number is 2.7, so 1 and 1, 2.7, and that's kinda where you can get your points from when you're doing your exponential, okay? And then you can just kinda run your line along that asymptote, and then you kind of get the angle that you need. Okay, so you just run it along the asymptote, coming smooth, and all of a sudden you hit that 0, 1 point, and then wherever your next point is on that line, again, that'll kind of be whatever your base is. Okay, and it says use the equation, example 3 down here. It says use the equation to determine whether each function represents exponential growth or decay. Justify your answer, verify your answer by graphing the equation in the graph calculator. Again, you can use Desmos here, and I'll just put that uh, right here beside it. Okay, we can use Desmos if needed there. But again, if we look right here, all you have to determine basically is what's the base. The base is E, so I know talking if we go back and look at our notes that you're looking at this value now. It's positive here. Okay, so this is going to be a growth. I'm just going to use tech because it's a lot easier. So this is a growth. Okay, 5 over 2. Now, this is a tricky one because it's a fraction, but 5 over 2 is actually greater than 1. So this one right here is also going to be a growth. And again, I'm looking at the 5 over 2 this time because it's not an E. Okay, now this one's an E, so now I'm looking up top. Since it's negative now, I know that's decay. Again, if we talk about what we said earlier, if you're looking at Desmos, remember a growth is gonna look like this. Okay, decay is gonna come from high and then fold out low. Okay. Again, this is not an E, so I'm looking, is it between 0 and 1 or is it greater than 1? Well, this is between. So I know this one's a decay. All right. I'm actually going to let you guys figure out these last 4 on your own. Okay. Use those things we talked about and see what would happen here on these different problems. Okay. If you guys got any questions for this lesson, just let me know. We'll have an assignment tomorrow on this. Um, go ahead and make sure you guys get all this written down. And again, if you got any questions, y'all just email me. All right, y'all have a good one.